Welcome to Computer Science 201. This is section 3.2, Predicates and Quantified Statements, part 2. The negation of a statement of the form for all x in D, Q of x is logically equivalent to a statement of the form there exists an x in D such that not Q of x. So if you want to negate a for every statement, it becomes a there exists statement. So symbolically, we would say if you want to do not for all x in D, Q of x, that's logically equivalent to there is an x in D such that not Q of x. So for example, hopefully the examples will make this feel obvious. We're going to write the negation of for all primes P, P is odd. Now that is not a true statement, correct? Because there exists an even prime. Okay, so the negation of this is there exists a prime P such that P is not odd. Okay, and this is true because x equals 2, P equals 2. This original statement was false. All right, let's consider the negation of an existential statement. The negation of a statement of the form there exists an x in D such that Q of x is logically equivalent to a statement of the form for all x in D, not Q of x. So the negation of an existential is a universal. Okay, so symbolically you'd write it like this. Negation, not there exists an x in D such that Q of x, logically equivalent to for all x in D, not Q of x. So for example, let's write negation of the negation of there exists a triangle T such that the sum of the angles of T equals 200. Now, we know that that's a false statement because there is no triangle that the sum of the angles would add up to 200. Every triangle adds up to 180. So the statement I've given is false. So I'm going to write its negation, which should be true, should have the opposite truth value. So using this rule right here, instead of there exists, I'm going to have a for every. So I would say for every triangle T, or for all triangles T, the sum of the angles. Now I have to negate that the sum of the angles is 200. So I'm just going to say the sum of the angles does not equal 200 degrees. And this is true. Okay, for all triangles T, the sum of the angles is not 200 degrees. Okay, so we'll do some practice with negating. And in these sentences, you'll notice that the quantifiers are implicit. So we talked about that a little bit at the end of last class. Well, sometimes you have to read carefully to determine what the quantifiers are. It can be helpful to rewrite it with quantifiers so that you can apply the rules for negating a quantified statement. So the first one is no politicians are honest. So I'm just going to say, I'm going to rewrite that using quantifiers. So this is the same as for all politicians P, P is not honest. All right, so then to negate it, so I turned it into a for every, which means its negation is a there exists. It would be there exists a P such that this is not true. So there exists a politician P such that P is honest. There exists a politician P such that P is honest. And the next one, the number 1357 is not divisible by any integer any, that's your clue that this is a universal statement, any integer between 1 and 37. So I'm just going to rewrite this as for all integers between 1 and 37. Actually, let's name it with a variable. That'll make it a little bit easier. For all integers n between 1 and 37, 1357 is not divisible by n. Okay, so I have not negated it yet. All I did is rewrite it using a quantifier. So this is not the negation. We just rewrote it. For all integers n between 1 and 37, 1357 is not divisible by n. So to negate it, I have a for every. Its negation is going to become a there exists. And it should be there exists an integer n such that the opposite of this statement. So 1357 is divisible by n. So my negation says there exists, looks bad, okay, there exists an n I'll be more specific. There exists an integer n such that between 1 and 37, sorry, be more specific, such that 1357 is divisible by n. All right, so I hope you noticed the negation of a for all statement is a there exists statement, and the negation of a there exists is a for all. And those facts are analogous to De Morgan's laws. Remember, De Morgan's laws said that the negation of an and statement is an or statement, and the negation of an or is an and. And this similarity is not accidental. In a sense, a universal statement is a generalization of an and statement, right? If it's true for all x's, then it's true for x1 and x2 and x3 and x4, right? And an existential statement is a generalization of an or statement, right? So if you're saying there exists an x, that makes something true, then either x1 makes it true, or x2 makes it true, or x3 makes it true. So for example, for all primes greater than or equal to 3, p is odd. So that's a for all statement, right? That's equivalent to saying 3 is odd, and 5 is odd, and 7 is odd, and 11 is odd, etc. If you just list the odds, if they are all odd, then you could use and statements to connect them. Whereas if you say there exists an even prime number, that's equivalent to saying 2 is even, or 3 is even, or 5 is even, or 7 is even, and keep listing the primes. Okay, the negation of a universal conditional statement. Let's derive it together. So universal conditional statement says that for all x, p of x implies q of x. That's just a universal conditional statement. Universal because it's true for all x's. Conditional is the if-then, or the implication. P of x implies q of x. So what we're going to do is negate it. We want to negate this whole thing and figure out what it's logically equivalent to. Okay, so we know that the negation of a for all is a there exists. So this is going to become there exists in x such that not the rest of the statement. So not p of x implies q of x. But remember, we've studied the negation of a conditional in a previous lesson. The negation of p of x implies q of x is p of x and not q of x. Okay, So we have there exists an X such that P of X is true and not Q of X is true. So I rewrote it down here as our conclusion. The negation of a universal conditional is there exists an X such that P of X and not Q of X. So let's use this to practice doing some negations. For all persons P, if P is blonde, then P has blue eyes. The negation says will become a there exists a person P such that, right? So there exists an X such that P of X and not Q of X. So the P of X is P is blonde, and the Q of X is P has blue eyes. So we take the P of X as is, such that P is blonde and P does not have blue eyes. Okay, so just to make that clear, P is blonde, this was my P of X, and P has blue eyes, this was my Q of X. My for all, the negation became there exists. So for all persons P became there exists a person P, such that P of X and not Q of X. It's a negation. Okay, if a computer program has more than 100,000 lines, then it contains a bug. So this one has an implicit quantifier. So I'm going to rewrite it. It says that for all programs P, if P has greater than 100,000 lines, then P has a bug. P contains a bug. Okay, so I just rewrote it. To negate that whole thing, I'm going to put a not in front. Okay, negate that. And so I have a for all programs P is going to become there exists a program P such that, and then P of X is P has greater than 100,000 lines, and Q of X is P contains a bug. So I have to do P of X and not Q of X. So such that P has greater than 100,000 lines and P does not contain a bug. So we finish up with vacuously true statements. Sometimes a statement is considered true just because its negation is false. So for example, I could say all dinosaurs living today are herbivores. We say that's vacuously true, right? Because there are no dinosaurs living today, so anything I say about all dinosaurs living today is vacuously true. And to make it even clearer why we call that true is we look at the negation. The negation will become a there exists. There exists a dinosaur living today that is not an herbivore, and that is false because there are no living dinosaurs, right? There exists a dinosaur living today? No, false. Thus, the original statement is true by default, and we call it vacuously true.